My name's Ben Richardson. I am a director of our sustainability team. I lead a lovely London bunch, and I'd like to tell you a little bit about this exciting adventure that we've been working on for the last 4 or 5 years now, I think. This largely covers UK residential schemes, but the stuff I'll show you now could apply to any building typology anywhere in the world, in theory. We've not gone that far yet, but we probably will in due course. And I do believe that our industry is slowly heading towards using data science and machine learning a lot more. And this is a really powerful, tangible example of how. Here's the agenda. I'll quickly go through a bit of background and some context in terms of the state of affairs. I'll only take up 30 minutes of your time in total. I'll then show you the parametric facade design tool that we've developed and give you a bit of a live demo of how it works in the game engine. And then as we go through, feel free to drop questions into the Zoom Q&A chats button. So, a bit of background, a bit of context. In my humble opinion, I don't think it's ever been harder to design a residential facade that works than now. And I think the reason being is we are in a world of challenging and very, very demanding parameters have been put on ourselves as a result of changing legislation, but also in the context of the residential world being financially challenged in terms of its viability, particularly as a result of things like double stair cores. Construction costs have gone through the roof of late. Cost of borrowing's gone up. And in London, we've also had a requirement for dual aspect apartments, which have thrown a few spanners in the works. And we've come across this particular trilemma of trying to make overheating, energy and carbon, and daylight work simultaneously on our facades. And it has got a lot harder as a result of this legislation change. We've had building regs in the UK updated in 2021, and consequently, Part L on the energy side and Part O on the overheating side are almost fighting with each other. One wants big windows and the other wants little windows. And then you've also got the context of local authorities wanting us to achieve certain daylight levels. There's a big pressure as well in London for us to hit embodied carbon targets. And these are all just minimum requirements. This is before we want to push boundaries and take our designs to the next level. And a lot of times recently, I've seen quite expensive cooling systems thrown in the mix to try and fix the problem, which it does fix, but obviously it has a consequence in terms of cost and carbon. And then with all that, we still need to be achieving a certain aesthetic with our buildings. And we've also got to balance it in context of those costs that I mentioned, and the viability challenges that we've had, particularly in the residential sector. So this led us to a few questions. How do we actually manage to keep those costs down, to keep these projects afloat financially, but still maintain energy efficiency and prevent overheating simultaneously? Or in other words, how do we optimize this facade design quickly to achieve all of those outcomes, but early on in the design stage and without it costing the earth? So it's these questions we set about answering 4 years ago, and we lobbied Buro Happold to invest in a research project that we've now seen the fruits of, and we're applying it, or we have applied it now on 3 or 4 specific projects. And it's called our parametric facade design tool. And I think this is the direction of travel for a few consultancies, generally speaking. But what it is we start with, in REBA stage 2, step 1, we set up a bunch of parameters that we'd all agree within the design team to explore. Then we'd go away and analyze those parameters and undertake thousands of simulations at the same time, and then come back a few weeks later, a second design team workshop, and present some of the answers that might work or might not, and give a bit of a solution corridor or solution window. And then step 4 would then be the architects taking that information away and working towards a design freeze. Then we'd take that design freeze at step 5 and do our final analysis, our final checks, as you would normally. And step 6 would be to produce an energy and overheating statement for planning. And these are the typical parameters we would explore. Down the left-hand column there, we've got a series of key parameters that impact the facade. Then we talk about the max and min range of those parameters, and you'll see the number of steps on the right there, which I'll come to in a second. So an architect might be particularly interested in, say, the window to wall ratio, and we've set something between 15 and 35% ratio on this particular job. Then an architect might also be interested in shading or not, roller blinds, and maybe how fat or thin the wall might be. But a cost consultant might be more interested in, say, triple glazing versus double glazing, or perhaps the mechanical ventilation system, and whether that has got a boosted flow rate or whether it's got a bit of what we call trim cooling in it. They might also be interested in the air permeability. So we set the scene and we run through these steps, and we end up with about 30 odd thousand different solutions. So then for step 2, we'd take those agreed parameters, we'd look at those glazing sizes or the glazed ratio, and we'd look at different G values and double glazes versus triple glazed. And we'd push those parameters into our software that we've developed. It's called BOM, Building Habitats and Objects Model. And that then allows us to talk to several official software platforms. So for energy and carbon in the SAP world, we use Argyle software, and it's a government approved piece of SAP software. For overheating, we use IES, which allows us to do the CIBSE TM59 analysis. And then for daylight, we use Ladybug and Honeybee to do those simulations. Then they get run, pushed to our game engine, which I'll share a little bit with you in a minute. There is the third step is collating those 31,000 results into this horrible looking graph. But essentially what we're looking at is the 3 outputs I've pulled out in this example on the right hand side, which would be overheating, embodied carbon, and SAP or energy. And then all of our design inputs on the left-hand side. And I could give you a quick demo of what this looks like in reality. So this is me filtering out some of the results on the right-hand side that I want to work. Then I might say, well, let's turn blinds off, let's turn shading off because we want to keep the costs down to start with. And let's turn off what we call trim cooling at the top here. Then we are left with some window to wall ratios and G values. So I can start with a certain G value, and I can see from this G value of 0.42 that the maximum possible window to wall ratio we can go to make it work, to achieve those cost-effective measures, is 25%. Now, if we drop the G value down, that does allow us to creep up to a 35% glaze ratio. So we can quickly use this tool in a workshop to talk an architect through the various options available to them and give a bit of advice to the cost consultant at the same time. And with data comes machine learning. And this is probably the future of building analysis. It's the future of how we design our buildings. But what it allows us to do is essentially teach the machine to interpolate between those three steps. And effectively what it means is those three glazed ratios that I showed of 15%, 25%, 35%, we can use machine learning to find the gaps and to be a little bit more bespoke or accurate with the estimation early on. Really, really insightful. And we've now got to the point where we've done so many models and combined so many projects, we've got enough data to not necessarily do any modeling. We've also pushed a load of energy inputs to the SAP engine, the energy engine. We've essentially modeled 3 million different residential buildings, which is roughly the size of London. And it means we can rock up on day one, look at the database, filter out some design solutions, and instantly give an architect a bit of guidance and a bit of direction as to what would work for those key outputs that you might be trying to achieve. And simplified, it might end up looking a little bit more like this. So we'd take a plan. This is before a design or a facade has been developed, and we'd mark it up, and using the data that we've got, this was a social housing example that we did a little while ago, we can give guidance on glaze ratios, but also what it means in terms of the number of units that would need trim cooling, which would potentially cost a little bit. So the ideal, a little bit more. So the idea would be to try and keep those numbers down. And this is all based on a collection of assumptions down on this right-hand side here. So we'd try and keep the assumptions relatively cost effective for this, in this example of this social housing model. That was the aim. And this would be for a very noisy site where we're forced to close bedroom windows at night under the UK Part O regulations. And so what I wanted to show you is then we could then push this to a game engine platform where it looks a bit like this. We're able to spin the geometry round. It might be a little bit laggy, and play with daylight levels to get a feel. But we can also dive into the geometry itself and say, look at each and every one of those 30-odd thousand daylight results. And as I zoom in, you'll see those daylight maps in each of the apartments. And up on the left-hand side here, this is our scale, if you like, of how well we're doing. So SAP is energy, essentially, or carbon, and we've got overheating. So we can, and we've also got a plan here to look at where the problem areas might live. And then down on this right-hand side, we can play with the glazing widths, and you'll see in real life the glazing widths changing, and also the glazing heights we can mess about with. And as we're doing this, the results are for daylight are appearing instantly in plan. And I can switch between daylight and, say, overheating. And this will be a pass-fail criteria, so it's quite easy to see the plan on the left-hand side here. I've got quite large openings at the moment. As soon as I close up the openings, you'll see a lot of the zone goes red because it's failing the TIBSI TM59 criteria. And so this allows us to take that parallel coordinate plots, that horrible looking graph, and make it a lot more it's a lot easier to engage with, it's a lot easier to understand, and it's a lot easier to see the impacts of the analysis. And it's live. A lot of the, well, all of those 30,000 results are here. And what we could do is come to a design team meeting with some presets. So we've got the previous scheme here, and we've found a particular set of results or some design criteria that's a bit of an all-rounder. So up on the left-hand side, you'll see the daylight creeps up, the energy creeps up and the overheating creeps up as I switch between an all-rounder and previous scheme. And so it's a really good analytical tool to try and find the answers pretty quickly, quite engaging as well. And so what? So what does this all mean? Um, it means that we can design out comfort cooling using passive measures quite early on. And some QS colleagues have told me that you're saving around about £5,000 per apartment for comfort cooling, and an additional £5,000 if you don't have trim cooling as well. And trim cooling is the cooling unit that sits on top of a mechanical ventilation heat recovery box. So there's almost a saving of about £10,000 if you could completely design out cooling per apartment, which is obviously not insignificant. Um, the client gets a more optimized facade design that works earlier on. So you're trying to resolve that trilemma a lot quicker, a lot earlier in the design process. You get reassurance around energy overheating, daylight, as well as embodied carbon, and the numbers to back it up. The architect gets a lot more early advice that is data backed, and a lot more constraints as to what works and what doesn't work before they get to a design freeze. So they've been finding it really effective to work to a constraint that they get confidence they know works. And the QS can get a lot more detail to inform a cost plan, especially if we look at across the, if we're talking about a medium rise tower block, if we look across different levels of that tower block, we can show the proportion of apartments that need or don't need trim cooling or don't need full cooling. So they can inform their cost plans a lot more accurately. And the biggest thing for us is that we have a less of a headache. We've been grappling with this subject for years now, and always seem to be causing ourselves a bit of a problem, and causing the design teams a bit of a problem. But it feels like we've really got to the point where we've resolved a lot of this using this tool. So it's really exciting. It's one of the um, most significant developments in my 20 odd year career that I've seen. And it's why we wanted to share a little bit more about it. And I do think it's the direction of travel for our world. You know, we have a lot of data about our buildings, and machine learning is becoming a much more significant part of not only our lives, but of design as well. And it just demonstrates how computational science and our data scientists that we've got at Buro Happold are becoming so much more um, useful and valuable to building design. So do please share your questions with me if you haven't already. First one, so how is it GLA compliant, and how will it not impact the accuracy of any assessment outputs? Okay, so because it's all done through government and official SAP engines, and because we use IES and CIBSE TM59 methodology, every single one of the 30,000 answers that pop out is an absolutely legitimate set of answers that can be used in an energy statement, and it's perfectly acceptable for the GLA. So there's no difference really in what you'd do normally. But added to that, we would also, I don't know if you remember in step, I think it was 6 of that methodology, we'd also recheck the final design freeze anyway. So belt and braces, if you like, using the conventional method. Good question. Next question, when is it best to use it? Yeah, I mentioned early design stages. Reba stage 2 is very effective, but certainly for planning generally, might be going to planning at Reba 3. could be useful then. Because obviously the benefit of trying to consolidate everything for planning in your facade is critical, because you don't want to get to Reba 3 or Reba 4, realize that your window sizes are too big and have to go back to planning with some sort of minor or major amendment. So to resolve it all for planning is super critical, I would say. Um, but it's also critical for value engineering. If we get to a certain point in the project and just wanted to reassess costs, it could be a really good tool for then as well. How reliable is it? So yeah, reliability to the first question, same sort of accuracy as well, it is exactly the same accuracy as conventional energy statement that would be delivered in line with GLA guidance. I suppose if we add the machine learning layer onto it, then technically we're interpolating, we're looking to guess the gaps between some of the answers we've got. So arguably less accurate using the machine learning bit, but we'd use statistical regression to sense check that accuracy and make sure that um, the advice is in line with the relevant procedures. But what happens when future home standard comes in? Yes, so obviously overheating, daylight, embodied carbon won't be impacted by future home standard, because that's predominantly a energy and carbon metric. But we would use is called the home energy model, and it will be open sourced. And our plan is to send those 3 million designs that I mentioned earlier, to send those to the home energy model and get that data back. So essentially, we'd have a new database, a new data pool for energy and carbon. £5,000 per watt. Is there subcategories for cost reductions? Yeah, this is so what I suppose one of our next step is to work with the QS, or a friendly QS that wants to be part of this, and build in those cost savings for each of those design options. So you've said £5,000 for what? So the £5,000 is what I've been advised is the uplift in cost to include trim cooling into each and every apartment. So if you could take that trim cooling unit out, it'd save you £5,000. And similarly, if we looked at, say, shading or roller blinds or G value or triple glazing, a cost consultant can put a number to each and every one of those, and we could almost have an output category for cost. Is something we've been trying to work towards. So yeah, good point. With a data set covering 3 million resi units, are you able to plug in new geometry and get an instant estimated performance using machine learning without the need to remodel? Yeah, so in theory, the whole point of having 3 million different residential units is we'll probably have every possible conceivable idea or design that an architect can think of before they've thought of it. So essentially, it would be a case of filtering out um, what the architect wants to achieve, and then plucking out of those 3 million units what's the most appropriate. And if and then we'd want to, we can layer machine learning on top of that and find the gaps in between those 3 billion units and create ourselves several 100 million units if we really wanted to. Good question. What game engine is used? Does it have another purpose than interactive view of the solutions? I don't actually know the name of the game engine. I'm afraid my techie colleagues have the answer to that. But we have been using it with our structural colleagues, with our MEP colleagues, to plug different outputs in. But mainly it's used for viewing solutions. In all honesty, it's not used for anything beyond that. Do you have product experience in hot, arid climate? How do you manage the climate situation? Yeah, we've not done this on in hot or arid climates yet, but it's relatively easy to put in new weather files into IES and create exactly the same data bank for a different place in the world. So that, like I said at the beginning, the concepts and principles could apply anywhere and to any typology. So yes, I suppose is the very, very short answer. Where acoustics determine windows must be shut during night, would you expect a fully optimized facade design to mitigate all risks of overheating without any mechanical cooling, or would you still expect some to fail? I would still expect some to fail, particularly those that are facing south, southwest, but also I'd expect them to fail because no one wants windows that are 10% window to wall ratio. We want to be able to achieve decent daylight levels. Um, we have seen the benefit of acoustic louvers and the benefit of things like roller blinds help with that situation. That gives architects a little bit more design freedom to increase glaze ratios. But ultimately, if you're closing bedroom windows at night and there is internal heat gain, you need to get rid of that heat somehow, and the ventilation system can only deal with a certain amount. So yeah, the aim I think with this is to simply just keep the amount of trim cooling we apply down. Um, Implementation into game engine looks very useful to drive design conversations. Do I understand it correctly? This uses the machine learning to produce the visualizations. No, it doesn't use machine learning to produce the visualizations. It uses machine learning to produce the results, and then we use the game engine to visualize those results. So yeah, we pre-run the analysis, but we're able to do it in, simulate those 31,000 results in um, well, a couple of weeks max. But we've also now got such a big database that we probably don't need to do any simulation initially, at least. And yeah, we'd love to expand into other sectors. We're looking at non-domestic. We applied this methodology to higher education building the last couple of months, and that's been quite successful. So we're trying and keen to push it on. I use this tool as well as any potential implementation collaboration with any of the tools. Okay, Autodesk Former, yeah. We've been exploring Autodesk Former, but I think the benefit of this tool in particular is just simply we can use the methodologies and the official software like IES, like SAP engines for energy, that's accepted by authorities and by building control. We've used those official software to get the answers out. Alrighty, sorry, I've gone over a little bit, but I think I've answered all the questions that I've seen. Thank you so much for your time. Um, do feel free to reach out to me. Details are on this last slide, ben.richardson@burohappold.com. So give me a shout if you'd like to understand a little bit more, and maybe if you want to collaborate or explore further. We'd be super keen to collaborate with people. So yeah, thank you for your time. Enjoy the rest of your lunch and speak to you soon. Thank you.